Okay, so this final test that we're going to cover in this video is again a chi-square test. It's a two-way classification problem this time, where we have two variables. We're looking to see if there's an association between these two variables as compared to where we just had the one classification table, where we were just looking to see if the expected frequency fell in the proportions that we predicted by our hypothesis. Now, in a two-way classification table, I'm going to use the same problem as the first one, except that we're going to make a distinction by age. So I'm going to now look at age. We're going to have two groups now, young and elderly, and we're going to have this morning, evening orientation of whether these people are morning people or evening people, and there are two categories there. So now we're going to look to see if whether you're a morning or an evening person is a function of your age. Are younger adults more likely to be morning people? Are elderly adults more likely to be morning people? And the nice thing about this problem is the degrees of freedom stay pretty straightforward. It's the number of rows minus 1, the number of columns minus 1, which is equal to 1. And now we set up our two-way contingency table. And we have morning people here, evening people here. We have our young adults here. We have our elderly adults here. We have 28 young adults. We have 14 elderly adults, and we have 42 people in total, 18 morning people, 24 evening people. So now these are our marginal totals, and we want to see if this distribution of morning to evening people and young to elderly follows in the cells here as well. So we would expect twice as many young adults as elderly adults to fall within these boxes. When we do that, we find we have 6 young adults who say they're morning, 22 who are assessed as evening. We have 12 elderly who were assessed as morning, and 2 who were assessed as evening. So this clearly sees these cell frequencies don't seem to be matching up with the marginal totals that we're expecting down here. Now, these are our observed frequencies. In the first problem we did with the chi-square, we actually had to determine the expected frequencies based on some hypothesis. But now we have the observed frequencies here. We can use these marginal totals to calculate the expected frequency. And it's a very simple formula. The expected frequency for each cell will equal to the column total times the row total over n. And once we get the expected frequencies for each of these cells, we'll be able to then calculate a chi-square test from there. So when we look at this cell expected frequency, it's 18 times 28 divided by 42, which gives us a value of 12. We look at this marginal this cell frequency here, it's 24 times 28 divided by 42, which gives us a value of 16. And you can already see that there's a discrepancy between the expected frequencies and what we actually counted when we surveyed our 42 respondents. We do the same here. 18 times 14 divided by 42 gives us a value of 6. And we do the same here. 24 times 14 divided by 42 gives us a value of 8. So now we've calculated the expected frequencies, we've calculated the observed frequencies. We can actually now put that into our chi-square formula. All right, so O is our observed frequencies, E is our expected frequency. We find a difference, we square it, divide by the expected frequencies, and sum it across our 4 cells. When we do that, we get so this is our calculations for our chi-square. We now calculate that value, and what we'll get is equal to 3 plus 2.25 plus 6 plus 4.5. When we add those values, these are for our 4. This is referred to as the residuals, the difference between our expected frequency and our observed frequencies. We add those residuals and they come to a value of 15.75. Now, that's our chi-squared value. Now we need to determine whether this is a significant effect, a significant association between these two variables or not. All right, so we go to our chi-square table and we look down the column which corresponds to an alpha or a significance level of 0.05, and we're looking at a degrees of freedom of just 1, which we calculated here. And when we do that, we look on the table and we'll see that the chi-square from the table is a value of 3.84. So our value is much larger than the one that is expected by chance, given a chance distribution of these cell frequencies is dependent on these marginal totals. Therefore, there is a significant association, which is pretty evident from our cell frequencies. If we look at our cell frequencies, there's more likely for the young adults to be evening, there's more likely for the elderly adults to be morning. So the morning-evening orientation varies as a function of the age of the respondent. Now, we're writing this up in an American Psychological Association journal using their format. We put our degrees of freedom in the bracket, and then we have our n, which is equal to 42. Our chi-square value, which we actually calculated, not the one that we obtained from our table, but the one we calculated, we get a value of 15.75. And this is significant at p less than 0.05. And if we look at the table, we'll probably see that chi-square value of 3.84, we could probably go to a smaller probability value, and this value would still be significant. I suspect we could go to 0.001, and that would still be a significant result. So yes, we did find a relationship or an association between age and the morning-evening orientation. The only problem with this is that the chi-square test, one of the problems if the expected frequencies get quite small, this is kind of acceptable, but when they get around less than 5, it starts to inflate the chi-square value, and people get a little bit concerned about that. Obviously, collecting more data would get around that problem. Sometimes if you have a lot of categories, you have a large contingency table. This is the simplest one you can have, a 2x2, but say you had a 10x10. You can aggregate the categories into larger groupings, and that gets you around this problem. But you do get concerned when you see small expected frequencies here. This is kind of acceptable at the moment. When you do get more complex to a table, say a 10x10, you're looking for patterns of where the association occurs, because these are, for the most part, usually qualitatively different categories. It can get tricky to determine what's producing this significant chi-square. Again, you can plot the residual differences and see where these patterns are falling. But probably the best strategy then is not to use a 10x10 table, but again to go for larger groupings of categories or break them up into smaller clusters, and then to do your chi-squares again with these smaller contingency tables. So that's our last statistical test in this course, the two classification variable chi-square problem.